Today we're going to talk about some similarity in right triangles. Before we talk about that, we need to talk about a special new term, a special equation that we're going to be utilizing in our similarity in our right triangles. So, if you remember from a couple chapters ago, I think it was last chapter, what is the special name for x and y? These two pieces are called the means. And A and B are called the extremes. So when I make those equal, I'm going to make x and y equal. You cross multiply. And remember, that's technically a property of proportions. I square root x equals the square root of A times B. That is called the geometric mean. So the geometric mean between two numbers is the square root of their product. So first example, find the geometric mean between 16 and 24. So the geometric mean between them, you find the square root of their product, 16 times 24. Well, I'm going to start breaking that down. 16 is already a perfect square. 24 is going to be 24 is 4 times 6. So I have 4, 2, that's going to be 8 root 6. So 8 root 6 is the geometric mean between 16 and 24. And again, that is useful to us for some theorems that we're going to have in this section. This is a theorem. This is a very, very important theorem that's going to help us find some interesting proportions, some interesting geometric means. So the altitude is drawn to the hypotenuse of a right triangle. The two triangles formed are similar to the original triangle and to each other. So what I personally like to do is I like to break these triangles down. I have the big triangle, as I call it. Triangle A, C, B. So then I have what I like to call these smaller triangles. This triangle here, that triangle, is also similar by angle because angle B is equal to itself. So that's angle B, that's angle C, this is angle D because that's where your right angle is. So B is equal to B in that smaller triangle. C, angle DCB, this angle up here, I mark with 2, that's equal to angle A. And then we have a third one, that is this one. And sometimes it takes people a little bit of time to see the similarities there. I always put the right angle down, that's D. Now angle A is equal to itself, or equal to itself in the big triangle. So therefore angle A would be up here, and then C is down there. So those are our three similar triangles. They're all similar to each other. So write a similarity statement for the triangles and then find TU. So our similarity statement, the big triangle, triangle TUV, make sure I can tell the difference between those if I were to ever give you this question, between the U and the V, similar to a triangle, similar to another triangle. So the big triangle is similar to this smaller one. Remember, the order matters. V is equal to itself, and that's our last letter, so that's V. The right angle is U, the right angle in the big triangle. The right angle in the smaller one is W, so that is the middle one. We're left over with U. And then the last one is this one. And that's going to be T, because angle T is equal to itself, W, and then U. So now I need to find TU. There's a couple triangles that we could use. I'm going to use the idea that TUV is similar to TWU. And what you might want to do is you might want to draw out your similar triangles over on the side. TUV. I know that that is 20, the hypotenuse. This is what I'm looking for. Draw out some other triangles. I said to use TWU. So TWU. So this is my U, this is my W, this is my T. TW, well, that's 13. TU is also in there, which is something that I was looking for. If I were to look at the other one, the other triangle, I would have W, U, and V. Do I know anything in that? The only thing I know in that is 7. So I don't know any of the other sides. So that's going to be harder for me to utilize in our proportions. So therefore, set up your proportion. TW over TU is equal to TU over TV. Then fill in what you know. TW is 13. TU is what I'm looking for. TU is what I'm looking for. TV is 20. Now cross multiply. I get x squared is equal to 260. X is equal to the square root of 260. I always want everything in simplified radical form. So I pull out a 2 root 65. Notice how x was in the geometric mean spot. Okay, the next one. This is how we're going to be utilizing the geometric mean. So in a right triangle, the altitude from the right triangle, opposite. The altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. So what that means is our altitude here divides the hypotenuse into 2 segments, AD and DB. AD and DB. So altitude geometric mean. The length of the altitude is the geometric mean. So the length of the altitude is CD. That is the geometric mean. That's why that was so important, of the lengths of the 2 segments. So BD over CD is equal to CD over AD, because CD was our geometric mean. And that was our altitude geometric mean. That's the abbreviation. Now we have our leg geometric mean. The length of each leg of the right triangle. So we're going to be talking about CB and AC. So those legs of the big right triangle are the geometric mean of the lengths of the hypotenuse, the whole hypotenuse, and the segment of the hypotenuse that is adjacent to the leg. So let's break that down a little bit. So it is the geometric mean. So let's look at this first proportion. CB, this leg in the big right triangle, is the geometric mean. So here and here, geometric mean across the diagonal from across the equal sign. So the geometric mean between the whole hypotenuse is AB, and the part adjacent to CB. So that part is DB. The other one, AC, the other leg, is the geometric mean between the whole hypotenuse and the part adjacent to it. So that's going to be just the segment of AD. So now we are solving for x. Okay, so let's look at this. Let's look and see what we have here. We have the whole hypotenuse. I have a piece of the hypotenuse, and I have a leg of the big triangle. Now the leg of the big triangle is adjacent to that little piece that we have. So I know that my leg here is the geometric mean. So it goes across the diagonals between the whole hypotenuse and the part that is adjacent to the leg that's the geometric mean. So I cross multiply, and I get x to be 3. Now solve for x. Think about what you're given here. You're given the altitude, and you're given the two pieces of the hypotenuse. The altitude geometric mean theorem says that this value x, the altitude, is the geometric mean between the two pieces of the hypotenuse. So 6 and 8. So now I cross multiply. X squared is equal to 48. I square root. We don't take the plus and minus here because we're talking about a length. So x simplifying our radical is 4 root 3. Okay, here are your lesson questions. Find the geometric mean between 2 and 6. I have a hint there. It says simplest radical form. So whatever the answer is, when you're trying to write square root, just write square root, and then in parentheses put whatever in the square root. And then you have 2 where you're solving for x.